Alright, in this video we're going to begin chapter 9 that deals with modeling our world. Our very first section, section 9a, deals with functions. And that's going to be the building blocks of mathematical models. Okay. Now, we're going to start off with a short review of the coordinate plane. I'm going to use this one. This is a better page. Here, the most common way to draw a graph of a function is to use what they call a coordinate plane, which is made by drawing two perpendicular number lines. Each number line is called an axis, and the plural is axes. So here we got two number lines, one going horizontally and the other one will be going vertically, straight up and down. Normally, numbers increase to the right on the horizontal axis and upward on the vertical axis. The intersection point of the two axes, where both number lines show the number 0, is called the origin. So here, that point of intersection here that I'm showing you is the origin. If we're working with general functions, the horizontal axis is called the x-axis and the vertical axis is called the y-axis. Now, points in the coordinate plane are described by two coordinates, which we call an ordered pair. The x-coordinate gives the point's horizontal position relative to the origin. Points to the right of the origin have positive x-coordinates, and points to the left of the origin have negative x-coordinates. Okay, so here your positive x-coordinates are to the right and your negative x-coordinates on the left. Now the y-coordinate gives the point's vertical position relative to the origin. Points above the origin have positive y-coordinates. That's these numbers here. And points below the origin have negative y-coordinates. Here we express the location of a particular point by writing its x and y coordinates in parentheses in the form x, comma, y. When working with functions, we always use the x-axis for the independent variable and the y-axis for the dependent variable. Okay, and in the figure on the left hand side, you're going to see a coordinate plane with several points identified by their coordinates. And note that the origin is the point 0, 0. Okay, so here are some ordered pairs that you see here. Like for 2, 3, they went to the right 2, they started at the origin, they go to the right 2, because it's a positive 2, and then they go up 3, and draw that point. For negative 3, 1, we start at the origin, go to the left 3, and up 1. And for negative 2, negative 3, we go to the left 2 because it's a negative 2, and we go down 3 because it's negative 3. And then for 1, 1, we start at the origin again, go to the right 1 and up 1. And for this last one, 3, negative 4, we go to the right 3 and down 4. Because 3 is positive, we go to the right. The 4 is negative, we go down. Okay, and then the figure on the right shows the axes, divides the coordinate plane into 4 quadrants, which are numbered counterclockwise starting from the upper right. So the upper right would be quadrant 1, where the x and the y coordinates are positive. Then quadrant 2 would be where the x coordinate is negative and the y coordinate is positive. Then quadrant 3, that's where both the x and the y coordinates are negative. And then quadrant 4 would be where the x-coordinate is positive and the y-coordinate will be negative. So that's basically what the coordinate plane looks like. Okay. Now let's look at this first example that is related to the coordinate plane. Like this one. They ask you to graph the points on the same axes. So here we got points A, B, C, and D. Now in the homework you'll be given a choice of graphs and they want you to pick the one that best fit those ordered pairs. I'm going to draw a horizontal and a vertical axis here. That way you can see what's going on here. Now in the homework you'll have to use that microscope icon or that magnifying glass icon to use to find out which is which. Okay, and in this case I'm going to have to extend my horizontal axis a bit because one of my ordered pairs okay. Now point A has the coordinates 4, 3. So when we plot the ordered pair 4, 3, what we're going to do here is we start at the origin, which is right here, and then we're going to go to the right 4 because the x-coordinate is 4. So we're going to go to the right 1, 2, 3, 4. The y-coordinate there is 3, so from here we go up 3 and draw the point. And we label that point as point A. And then for point B, which is negative 7, 2, we start at the origin. We're going to go to the left 7 because it's a negative 7. So we go to the left 1, 2, 3, 4, 5, 6, 7. And my y-coordinate is 2, so I go up 1, 2. Draw the point, and we'll label that as point B. And then point C is 0, 0. That's the origin right there, so we're not going to go to the left or the right, and we're not going to go up or down, so that's the origin right here. So we label that as point C. And then D, negative 3, 1. Start at the origin, go to the left 1, 2, 3, and then go up 1. Label that as point D. Now, based on this graph here, we're going to pick the one that's closest, that looks like the one that I just drew. And by looking at this, it will have to be, in this case, graph D, because I know that A is in the first quadrant. Because A has the ordered pairs 4, 3, where the 4 is positive and the 3 is positive. The x and the y coordinate are both positive, so I had to pick this one. Okay, that's just a short synopsis of how to plot ordered pairs on a coordinate plane. Okay, let's talk about language and notation of functions. Functions tell us specifically how one quantity varies with respect to another quantity. In this section, we will explore the language and notation of functions. Okay, so we're going to talk about dependent and independent functions here. The quantities related by a function are called variables because they change or vary. The dependent variable depends upon or depends on the independent variable, which is the variable that changes or varies. Okay. So the independent variable does vary and it does change. The dependent variable will usually depend upon what the independent variable is, specifically when we're dealing with a function. Now, in example 2, we're going to state whether two variables are related in a way that might be described as a function, and if so, identify the independent and dependent variables. In this case, you run different distance intervals on a track and want to know how your heart rate depends on the distances you run at a fixed speed. Now here we can describe that as a function, because here the dependent variable is going to be the heart rate, because it says here your heart rate depends upon the distance you run. So the distance will have to be, in this case, the independent variable. So I'm going to choose this first answer choice, answer A. Okay. Here's another example. We're going to state whether the two variables are related to each other, related in a way that they might be described as a function. If that's the case, identify the independent and dependent variable. You run an electronics store and want to know how the quantity of TVs you sell depends on the price you charge per TV. Now this situation can be described as a function in this case. As you can see here, your independent variable will be the price that you charge per TV. And the quantity of TVs that you sell will be your dependent variable. So in this case, I'm going to pick this answer choice. The dependent variable is the TV sold. The independent variable is the price. Okay. Alright, next we'll talk about what functions are. A function describes how a dependent variable changes with respect to one or more independent variables. When there are only two dependent variables, they are often summarized as an ordered pair with the independent variable first. So here the independent variable comes first, your dependent variable comes second in the ordered pair. So the dependent variable is a function of the independent variable. If x is the independent variable and y is your dependent variable, we write the function as y equal f of x. Okay. So now, example 4. Here we're going to write a short statement that expresses a possible relationship between the variables. So here your independent variable will be the volume of the gas tank. Your dependent variable will be cost to fill the tank. So we want to choose which one will best describe that relationship. Well, if we look at it, we can see that if we increase our volume of that gas tank, the cost to fill the tank will increase. So here I'm going to choose answer B. As the volume of a gas tank increases, the cost to fill the tank will increase. Okay, and that does make sense. Okay, all right, let's look at this example, number 5. Here we go. Here we're going to write a short statement that expresses a possible relationship between the variables, like time traveled from Denver to Chicago and average speed of a car. And we want to select the one that would best fit that situation. So here your independent variable will be the time travel, the travel time from Denver to Chicago. Your dependent variable will be the average speed of a car. Well, let's think about this. If the average speed of a car increases, then your time to drive the car from Denver to Chicago is going to actually decrease because you're increasing the speed. The faster you drive, the less time it's going to take for you to get from Denver to Chicago. Okay? So we're going to pick that answer choice right there. As the average speed of a car increases, the time to drive from Denver to Chicago will decrease. Okay. All right, here's another example. Write a short statement that expresses a possible relationship between the variables. So here we got the rate of pedaling and speed of a bicycle, and we want to find out that which one will be the best one that explains that possible relationship between those two. Well, if we increase our rate of pedaling, then the speed is going to increase as well of that bicycle. So here I'm going to pick this answer choice here. As the rate of pedaling increases, the speed of the bicycle increases. Okay. Alright, now let's talk about how to represent functions. There are 3 basic ways to represent a function. One, we can use a data table. Okay? So we have a data table like X and Y. Let's say it has something like this. There's a table of X, Y values here. That's one way of representing a function. Also, we can draw a picture or a graph. So in this case here, if I draw an XY coordinate plane like this, using those ordered pairs that I have, here I can plot 0, 3 like this, and then 1, 4 to the right 1 and up 4, and then negative 1, 2 will be to the left 1 and up 2, and negative 2, 1 will be to the left 2 and up 1. So if I was to connect those points, this would be the graph of a function. So here we can draw a picture or a graph. And then write the equation or formula. That's the third way of representing a function. This is actually the equation y is equal to x plus 3. This line right here is the graph of the linear equation y equal x plus 3. Or we can say f of x equal to x plus 3. Here f of x and y mean the same thing. Okay, next we'll talk about domain and range. Now the domain of a function is a set of values of the independent variable that both make sense and are of interest for the function. And then the range of a function consists of the values of the dependent variable that corresponds to the values of the function. In other words, your domain, if you had a set of ordered pairs, your domain is going to be all of your x values here. And then the range will be the set of all y values. Okay. Alright, now if we want to create and use graphs of functions, there are 4 steps. Number 1, you want to identify the independent and dependent variables of the function. And then step number 2, identify the domain and range of the function. Use this information to choose the scale and labels on the axis. Zoom in on the region of interest to make the graph easier to read. And then step number 3, make a graph using the given data. If appropriate, fill in the gaps between data points. And then finally, step number 4, before accepting any predictions of the model, be sure to evaluate the data and assumptions from which the model was built. Okay. All right. Now, if we look at example 7. Here we're going to use the graph on the right to answer the following questions. In part A, estimate the pressure of altitudes of 6,000 feet, 12,000 feet, and 21,000 feet. Okay, now, in the homework, there is going to be a icon that's of a magnifying glass. You might have to click on that, or I think there's a button where you have to press and then it'll pop up this screen. It'll blow this graph up a bit so that way you can see it a little bit better. So here the pressure at 6,000 feet is what? Well, we know that's 10,000. And this right here is at 5,000. So if we go a little bit further at 6,000, I know at 5,000 is 24, so we're going to have to kind of guesstimate just a little bit. The pressure at 6,000 feet is, okay, and we're going to have to say about 24 inches of mercury. And the pressure at 12,000 feet would be, well, here's 10,000, that's 22. So if I go a little bit further, it's going to be a little bit less than 10,000. So that pressure would probably be about 21 inches of mercury. And the pressure at 21,000 feet, well, at 20,000 feet it was 16, so it's got to be a little bit less than that at 21,000 because this graph is decreasing. So I'm going to say about 15 feet of mercury. Okay, but here on the homework you'll just have to blow that graph up using either that magnifying glass or that other icon that they have. I'm not sure what it is, but it does allow you to blow the graph up so that way you can see it a little bit better than on the paper. Part B, estimate the altitudes at which the pressure is 23, 16, and 13 inches of mercury. So in part B, we're going to find the altitude for which the pressure is 23 inches. So it's between 20 and 25. That would mean it would be about, I'm going to say approximately 8,000 feet. Because here's I'm going to say 23 is about right here. If you go across here to that point there and then read down from the horizontal axis, it will be less than 10,000, which I'm going to say 8,000 feet. And then the altitude for which the pressure is 16 inches, where here's 15. 16 is one more than that, so if I read across on that point and then find that's close to 20,000. So I'm going to say about 19,000 feet. Okay. That's where the altitude for which the pressure is 16 inches. And the altitude for which the pressure is 13 inches, that's between 10 and 15. That's on the vertical axis, so here I'm going to go across. I know it's got to be between 20 and 30,000, which will be, I would put it at 24,000 feet. Okay. So these are just estimates here. Now part C, the altitude at which the atmospheric pressure reaches 5 is approximately what? Well, here's 5 right here, and we're going to have to kind of guesstimate a bit here, because if this continued, then in this case we will say approximately, and I would say approximately 40,000 feet if we were to extend the horizontal axis. Okay. And then part C, estimating beyond the, well, we've already done that. That's part C right there. Now here we're going to explain whether there is an altitude at which the pressure is exactly 0, and choose the correct answer below. But based on this, you're not going to have the altitude at which a pressure is going to hit exactly 0. It will approach 0, but theoretically it's never going to reach 0. Okay. Alright, now example 8. The last example in this video. The following table represents a function, and we want to identify the independent and dependent variables and describe the domain and range. Okay, so in part A, we want to know what the independent variable is. With these, you're going to have a drop-down menu to select the correct answer here. Your independent variable is this right here. It's the speed. Okay, so it's the first column. That's your independent variable. The dependent variable will have to be the stopping distance, because that usually depends upon the speed. Okay. Alright, and then the next one is the domain of the function consists of all of the, well, the domain is going to be this right here. All of the speeds. Okay? That's your domain. From the minimum of, well, the minimum speed is 10, to the maximum value, or the maximum speed in this case, that's going to be 70. So from 10 to 70. And then the range of the function consists of all the stopping or distances. Okay, because if the domain is your speeds, then the range has to be your distances. And that's from the minimum value of, in this case, the minimum value you see here is 11, to the maximum value, as you can see here, is 305. Okay. Now here you're going to make a clear graph of the function, and you're going to choose the one that fits that particular table on the left-hand side. In this case, you'll have to blow each one of those graphs up to see which one will best fit that table, and it will have to be this one. Okay. And sometimes you have to do trial and error here, or process of elimination. I know it can't be D because the stopping distances are increasing. This graph is decreasing from left to right. And part A is out because I know in part A you got a straight line. Okay? The differences between the stopping distance are not consistent. And then finally we choose the correct description below. So we have to select which one fits that situation here. And it's going to be the case here is that the rate at which the stopping distances increases grows faster as the speed increases. Okay? Because as you can see in that table, they're increasing rapidly. So pretty much you have to read through that and find out which one will best fit that particular situation. Okay, so that will complete this video on functions, which is the building blocks of mathematical models.